last 2 Uhr today, and also last class. So next week I'm going to a conference in Germany, and there will be no class. So
is it the same conference that Eli Balkai is going to?
No, I doubt it. Yes, he's also going to Germany.
I don't know. He's going to some conference.
Okay. There are many conferences. So as soon as the summer starts, we are busy going to conferences. Take the time to work on the last assignment that you will get maybe tomorrow, right?
Yeah, maybe today.
Maybe today.
Yeah,
maybe
we'll
today. Maybe tomorrow. And because we don't want to extend too many times the deadline, okay? Because now all the time we extend the deadlines, but after I'm back from the conference, I want to get the grades from Dimitri and be submitted to Madrid that they can get your dots ready, right? Because usually I'm not submitting by beginning of August, then there are students complaining because they want to go somewhere else and they need their certificate. So we won't extend too much the deadline. Okay, so use next week to work on that.
Yeah, I think we will do as usual 1 week to do assignment, and then maybe if someone
2 weeks we do usually, right?
Yeah, 2 weeks.
Okay, yeah. So
basically maybe
if we get today, then maybe
beginning of July, maybe
10 of July.
10 of July max. Yeah.
Make the deadline.
Yeah.
Okay, good. That you are prepared.
Yeah. So last week you talked about time series analysis. Today we're gonna repeat some of the ideas that how you can analyze a time series, what time series, how does it look like, and all these structures. And in the end of the tutorial, we're gonna see if we can make some money out of the random fluctuation analysis and the Hurst bond. Okay, so we're gonna analyze S&P 500 and the Apple stock price, Bitcoin, and see if there are some strategies that can give us money. Okay, so but before that, we'll do more boring part. We just simply look at the anatomy of time series. So time series usually has several components. So this, you can see this just observed data, and there is some observations of, I don't know, temperature or carbon dioxide emissions, something like this, over time. And you can basically decompose observed signal by 3 separate time series. The first one is basically trend. The second one is seasonal component of periodic function. And if you subtract these two from observed data, the rest is noise or random part of the signal, or alternatively you can call it residuals. Okay, and usually the most interesting information. By the way, do you know in what part of this decomposed time series the most useful information sits? No ideas.
Depends on what you consider important.
Yeah, exactly. That's the answer that I expected. So, for example, if you do, like if you sell in ice cream, okay, you only care about basically the seasonal component, right? You have in period of summer you have a peak of selling because it's hot outside and people buy ice cream more, and in winter it's less probable that someone will buy ice cream, right? So if you make a model that can accurately predict this seasonal change, that's good for you. But for example, if you're created a website and you sell some products online, okay, you can see that there is a trend in your data. So every month you sell more of your product, and that's good. And there is also going to be some seasonal component. And if you go deeper and analyze the noise component, say that this part of the signal can tell you that this happens because, let's say, you had some problem with a payment method on your website, and that's why the selling dropped. And this peak can, be because of some influential tool plugger just mentioned your brand. So the answer to my question is really depends on what you consider as important, right? And
but you could ask in what of the steps is the least obvious information. Okay, I mean a trend, some periodicity, it's kind of obvious, but in the residuals, it's not straightforward to see, right? Is there some information that is
in residual component, it could be both sides, right? If you have here white noise has no information inside it. But if it's like some persistent signal or anti-persistent signal, and it can give you some insights about the time series. Okay. So during this tutorial, we're gonna mostly work with this random component of time series. Okay. So the first feature that we're gonna calculate is autocorrelation. So we build autocorrelation function as a division of the first moment of shifted signal by S minus average and times signal itself minus average divided by variance. Okay, and by just definition of autocorrelation function, when S, so basically the lag is 0, you have your variance divided by variance, which always equals 1. And for white noise, you have no memory in signal, and autocorrelation function for S non-equal is not 0, simply 0. Okay. So here is the graph of white noise. So you can generate it by a simple Python library, random, and here is the white noise itself. Here is the cumulative profile of this white noise. Basically, it's like integration of this signal and autocorrelation function. So as you can see, at S equals 0, autocorrelation function is 1, but then just one step out of from 0 gives you 0. Then it's the same everywhere. Okay. And now the question is how we can change this memory of the signal. So the answer is we can play with first exponent. Okay. Last week you talked about first exponent as like a single number that can describe memory of the signal, and you can see that here I also generated signal with positive autocorrelation. So the signal remembers somehow its past, and you can see now the cumulative profile looks differently compared to the white noise. So when we have white noise, it fluctuates a lot, even this small region. But when you have Hertz exponent of 0.75, now signal is smoother than for white noise. Okay, so it means that signal remembers it past, and if here I have decrease, right? So it keeps doing so till some point. Okay, and then there is a uptrend, and that continues to go so, right? And I can put even higher Hertz exponent to make it even more smooth. So let's see how signal will change. Yeah, so now it looks like even one line, right? And autocorrelation function decreases much slower than for white noise it's exactly 0. But here, if I put, let's say, 0.65, yeah, autocorrelation function decays much faster. And the other case is anti-persistent or negative autocorrelations, is then Hertz exponent smaller than 0.5. And you can see that signal becomes even more rough, and almost everywhere changing its the direction, right? Autocorrelation function here become negative, and then it also drops to 0 faster. Any questions here? Okay. By the way, what if I put here Hertz exponent of 0.5? What do I expect to happen?
1.5?
Yeah, just 0.5. 0.5. That's a simple question.
Just talked about it.
Yeah. So we have two regimes, right? If my Hertz exponent bigger than 0.5, I have persistent or positive autocorrelations. Signal is smooth. Okay. The Hertz exponent smaller than 0.5, I have rough signal and negative autocorrelations. And what happens in this exactly when h exactly 0.5?
White noise.
Yeah,
Yes.
white noise, exactly. So you
First picture was white noise.
yeah. So even though I
Just called it white noise, but it's
yeah,
most explosive.
white noise is like the point that splits these two regions of positive autocorrelations and negative autocorrelations. In between you don't have any correlations at all. They not positive and they are not negative. Okay. The second feature that we're going to calculate is correlation time. So correlation
One second. If you would do a power spectrum, we also talked about Fourier transform in the last week. If you would do a power spectrum of white noise, how would it look like? Take a white noise time series and you do a power spectrum. You can do a power spectrum of everything, right? It doesn't need to be strictly periodic. What would happen? How would it look like?
Just to give you a hint, power spectrum basically shows you what contribution of every frequency you have in the signal. Okay, so we know that white noise has all of the frequencies, right? So we generate them randomly. So there is no specific frequencies that contribute more than
uniform.
yeah.
Yes,
It's a uniform distribution. You have every frequency has the same influence to in the signal, so the same contribution. So that's why if we gonna plot power spectrum of white noise, it's gonna be like a line, okay? Just uniform distribution.
Good. Nitai, follow-up question. Now you want to do a smooth signal, like Hertz exponent of 0.9. What do you do?
What do you mean this?
Hmm?
From a Fourier series point of view?
Yeah.
You take exactly just one frequency, for example.
Yeah, or you are kind of you have your
Yeah, you lower all of the terms and take
you
one
lower
big, like delta function.
you lower all the high frequencies.
Yeah.
Because this is what makes it a noise, and you increase the low frequencies, right? So you kind of change the slope in the power spectrum.
Yeah.
And that's exactly a method to generate autocorrelate signals. Very famous method by Havlin and Maxe many years ago, and they do exactly this, very easy. And we will talk about this a little bit later.
Yeah.
Can I ask a follow-up question to that?
Yeah, great, please.
If we do that, then we would only know information about the trend. Would lose information, for example, about periodicity, right? Because when we take like only the lower frequencies, we'd see the smooth function, and then we'd understand only the general.
No, but you can have on top of this still some periodic. It's flat for white noise, but if you now put.
But if you do like peak only in the, let's say,
Yeah, you
I
can.
don't know, 10 first like biggest frequencies, and then you
Yes.
shut everything down for 0.
Yeah,
Then
you
you'd lose.
You lose the periodicity
Yeah, exactly.
of the graph itself. You cannot
Yeah, you
example,
have
Ah,
only
okay,
strength.
yes,
sine times
Yes.
also, and you have,
Right.
Yeah, you lose the
Okay.
oscillations.
Okay, yeah, this that's good. Yeah. Right. Okay.
Yeah, the next feature that we're gonna calculate is correlation time. Basically, it's the characteristic time scale of our time series. Okay, and by definition, it's basically first moment of autocorrelation function. Okay, so we just have to calculate this integral, and there are two types of time series. The first one is with short range memory, and the other one with long range memory. One with short range memory tells you that your autocorrelation function decreases as exponent, okay? And long range correlated signals, they usually have autocorrelation function that decreases as a power law, okay? And we expect that if autocorrelation function behaves like a power law, this integral will diverge, okay? Because from very first lecture and the tutorial that we have, we discussed that power law has no characteristic time scale. I mean, no characteristic scale. And the first moment and second moment diverges.
This is actually, sorry for the interruption. So this is actually what happens spatial. I mean, this is a temporal thing, but spatial in
space.
3D in space, right? At the phase transition, right? I mean, this is what Ginzburg-Landau theory is all about. That when you go to the critical point, that your correlation length in the system diverges. This is exactly the same thing. Here instead it's with time, there it's with correlation length, right? So just for you to connect it.
Yeah,
you learned about Ginzburg-Landau and
There was a
critical exponent.
now.
so you don't have statistical physics with phase transitions and
graph based on
No, you
Yeah,
know
but
about
then we
Ising
have
Ising
the
model. You
critical-
know about
the Ising
Ah,
model.
okay.
yeah.
so-
So
it's you also see it in the Ising model. It's the same thing, but Ginzburg-Landau describes it.
Wait, so what would be the criticality?
You have so that's the interesting thing, that you have basically a critical point in time. So it means when you find this for time series, right? You find for time series that, for example,
Before the market explodes or something? Before the market explodes or something?
or for the market. No, I don't know. I'm not so good in
Or the
economics.
2008 collapse?
we're gonna discuss it.
Yeah, we're
okay.
going to discuss this, but I don't know about this. But in physiology, for example, it means so what you get there is in cardiac dynamics, for example, you see also your correlation time diverging. So that means that there's a big theory about this fractional physiology, that the human organism at a healthy state is always at a kind of a critical point, you know?
Self.
Yeah, it sounds,
Can become unhealthy.
it sounds very, very
As
strange,
it-
but it makes sense if you think about it. So when you are at the critical point, when the system is at the critical point, it is most susceptible to external perturbations, right? It can quickly adapt. And when you look at, when you take time series, physiological time series of sick people, you see that they are away from the critical point. And this also makes sense somehow. It's difficult for them to adjust. Send up a cardiac patient up a couple of flight of stairs. It takes him half an hour to recover from this, right? Whereas you're running and afterwards you're fine, right? So that's the philosophy behind temporal criticality. Okay.
Yeah. I mean, in terms of this Eisen model, when you're close to criticality, there is a power law, right?
Yes.
And correlation length diverges, and therefore your information propagates through the whole lattice, right?
Yeah,
Like
you
it's
said this
spread
spin,
out the spin,
the spin on this side of the lattice feels the spin on the other side of the lattice. In cardiac dynamics, they say the heartbeat that you have now is correlated with something that you will have in the evening, you know? I mean,
So this happens because of the mean field approximation? Because, I mean, by nature of this mean field, you basically assume that it feels all the same from around the lattice.
And what is mean field? What is this mean field in the human organism? The autonomic nervous system. That's the kind of the mean field. You know, that is kind of regulating and averaging your all your inputs and your outputs and stuff like this. But it's too much for one lecture, but it's interesting thinking. You know, the parallels between this. Okay.
Yeah. So and there are two kind of behaviors. If this integral converges, it means that there is a short range correlations in the time series, and if this integral diverges, it means the opposite, that there is a long range correlations. And here you can see that for long range correlations, the absolute value of correlation function as a function of leg S is indeed a power law, right? So here I put first exponent of 0.9, and you can see that we have quite noisy tail. Can you suggest a solution how we can fix this?
I first ask them, why is there a noisy tail?
Okay, why there is an edge? Follow-up question about noisy tail.
Maybe you show them the formula. You see it on the formula, not on this, on the correlation, what the correlation function. Here. See it here. Right, there is a fluctuation, a big fluctuation at the end. It's purely statistical. So when you have large gaps, right? S is the gap. So if you have a little gap, if you just compare neighboring elements in the time series, you have a lot of statistics to average over, right? If you take a big gap, then you don't have much to average. I mean, if you take hundreds of seconds apart, then maybe you average over.
So law of the large numbers. Law of large numbers. So once you have low,
so if you have large gaps, you have less statistics, so it starts to fluctuate a lot, and this is a problem because you are especially interested in what happens in the tail, but you cannot look at the tail because the tail is fluctuating.
So at
why go down?
Why go what?
Why is it going down?
Because it's
Why not up?
it can also go up. So in the end, you see it goes up. It's just.
So the solution would be to add samples to make it.
No, the solution is. I mean, here you can only reliably say something until 10 to the power 2, right? Until 100, even less maybe.
Yeah.
So the solution is to do a fluctuation analysis or detrended fluctuation analysis. Then you don't have this statistic problem.
Or you can
Or maybe
basically,
he has another solution.
yeah, you can basically calculate this, generate this many times, and just do average of these samples.
But you get only square root of the of drives. Usually.
You mean error
The error.
drops like 1
Yes.
over.
Yes.
I mean, again, it's not perfect, but you can define a cutoff to, you know, to make your fit better. Okay. And then I just want to show you that we can prove this the integral divergence of this integral when you have long range computation. Okay. So instead of calculating the first moment, I'll do it for 0th moment. So basically, without s extra s here in the integral, and my goal is to show that if I have here a power law, so s the autocorrelation function behaves like a power law, this integral will grow as function of s. Okay, so and eventually, if I have integral from 0 to infinity, this integral for long-range correlations will diverge. Okay? And I compare it with short-range correlations. So now, here is the picture. That's how this integral behaves as a function of upper cutoff. Okay, you can see here, orange one is short-range, and blue one is long-range. This dashed line is a theoretical result for h for her exponent equals 0.75. Okay, here's the relation. So correlation functions behaves for long range as a power law s to the minus gamma, and this gamma is connected to Hurst exponent as 2 minus 2h. Okay, so if h equals 0.75, gamma has to be equal just 0.5. And if we integrate it, then we expect TFS be square root of lambda. Okay, and if your integral goes from 0 to infinity, then it diverges when s goes to infinity, right? But here we can see some deviation from it, and if I play with the upper cutoff, so what I expect if I increase cutoff, the orange line will.
What are the lines?
Hmm?
What are the lines?
I said that blue line is integral, this one, when you have power law, basically it's long range correlations, and the orange one is short range correlations, the same two integrals. Okay, for orange line we expect it to converges because its short range order is exponent to some power, and it decays, and then for blue line we expect that it will diverge. Okay, so let's increase let's increase power cutoff. Now it's 200, and let's do it 2000. Okay, now I increase it, and I expect that again blue line gonna continue to grow, and yellow one will decay.
And the blue line is which gamma again? I mean, is it or which?
Gamma of 0.5, and then I integrate it.
But then it should actually coincide with your dashed line.
Yes,
Okay.
exactly. So
it
dash
should-
line is theoretical, but
Yeah, so why doesn't it?
computation,
That's the
yeah, computationally we have somehow decreased.
question. Even goes down.
Yeah,
Why is
and
this?
if I do like 4,000, so I'll double the current lag. You can see that it
So
drops.
something is wrong.
Yeah,
Right? Something is wrong. It has to diverge.
yeah. Any ideas why we have such a behavior?
You have some elbow in your calculation.
Is it because there's a limit on the sample size that limits how big S we can check?
yeah, you have like, look, here we have number. I mean, our time series has 4,096 points, right? And if number of legs approaches to the number of points in our time series, I expect that I will gain some error, estimation error, right? And if you go to the definition of autocorrelation function, so what happens when I increase s? First of all, I have a mistake because I have less statistics, and the thing that is more important that how I estimate mu. Mu is my average value of time series, okay? And if I have, if I estimate it from the same series that I have, then it's not true mu for infinite time series. So I introduce some bias into my data. So one of the solutions is to either keep number of points in time series much larger than upper cutoff. That's one solution. Like I had here original with 200 points. Yeah, here. I mean, looks almost perfect. And the other solution is to work with exact computations. So we will not simulate the data. We just look at theory, the notebooks, and we will see that for autocorrelation function, it scales as a Hertz exponent with this formula. Okay, here is a function of lag, and you see here Hertz exponent, and we know how it works for short range correlations too. And now we can plot them just theoretically, and you can see that now it perfectly aligns with theory. Okay.
Why did it go down in the first graph?
This one,
In the previous?
the one before.
Yes. Why did the blue line go down and not become flat?
Because again, you have basically in the definition of autocorrelation function, you have to calculate a first moment and you using here mu. Okay, if you compute mu from the same time series, then this sum is going to be 0 because x bar you basically calculate from the same data, right? And then you can show that if you calculate the integral of your autocorrelation function with every lag that you have, it will converges to minus 1 half. Okay? And that's why if I increase your number of points, if I do exactly the same number of points that I have in my series, then I expect. Okay, let's do one less.
When you have only one window, your variance is 0. So then
Yeah, and you can see that it converges not to 0, but
no, at the end it converges to 0 because you only have one window. Then the variance is 0.
I'm talking about this one.
The blue one, yes.
The blue one.
Yeah.
The blue one converges to minus 1 half.
Minus 1.
According to this. So you can prove it mathematically that converges to minus 1 half. But that's because of finite sample size and you calculate the expectation of a signal from the same data. Okay, and then self-affinity and the Hertz exponent. Hertz exponent basically shows you how your signal scales if you zoom in or zoom out. Okay, and there is a way how we can estimate it with fluctuation analysis. In a nutshell, it works as follows. we have a signal with Hertz exponent of 0.75. So we expect that the signal has positive vertical relations, and we compute cumulative profile, and we use different scales. Okay, here we can see the increment distribution for different scales. So we basically pick different window sizes. Okay, for 4, for 16, for 64, 156. Okay, and finally, from every window, every scale, we compute residuals, fluctuations, and these fluctuations scales as a function of window size. And
so basically you zoom out, right? You took the lower and then you no, you zoom in. Can you go up? So this, so from the top, when you go from the top.
Yeah.
Okay, now you zoom out, right? You zoom out and out and out. Okay. So you go down and zoom out. Okay. The increment, the distribution of the difference is always the same.
Yeah.
Okay.
So, and that's basically the what this fluctuation analysis does, right? We have 4 steps. The first one, we remove mean out of the signal, then we calculate cumulative profile, then we split the signal into non-overlapping windows. We calculate standard deviation of every segment, and then for self-affine time series, we have this fluctuation function fs scales as a power law with the scaling exponent of h. And there are three kinds of behavior. First one, h equals 0.5, it's like a random walk or white noise. Then h between 0.5 and 1 is persistent positive vertical relations, and the opposite limit, then h greater than 0 and smaller than 0.5, you have anti-persistent or negative vertical relations. Question?
Yeah. In when you say self-affine series, you mean like a series that, like, if it already trends in one way, it will trend more, or like what do you mean when you say self-affine series? Like
that you can zoom in, okay, and you see kind of the same patterns.
Oh, so self-similar, like
a fractal. You can measure with fractal dimension and percolation. I mean, every topic of this course is somehow connected with others, so you can build mind map, basically a network, and structurize your knowledge in this. Okay, and but the problem with fluctuation analysis is that it doesn't take into account trends. Okay, so here what I did, I have basically white noise with Hertz exponent of 0.5, and I added to this white noise just a tiny linear trend. Okay, it's t times 10 to the negative 5, very small. But you see how this teeny tiny trend affected our estimations of fs. So it shifted somehow fluctuation function, right? And now if I fit these points, I'll have greater value for Hertz exponent, right? Here is a true value of 0.5, and if I fit here, then I'll get something around 0.6 or 0.65.
But maybe taking h to be 0.65 generates the data with higher probability. Like you added a trend.
You want to try to have 0.65 here? Okay, let's see. So let's do.
Actually, it converges to 1. What did you put now?
Now h is. I mean,
85.
the closer you to 1, the more persistent correlations are, right? And therefore, trend like has smaller contribution, right?
Yeah.
Because signal is already remembers it past better, so that's why if you closer to 1.
But you will still get, for larger scales, if you go to scales beyond this, to 10 to the power 3 or 4, then you still have deviations, you know. So
yeah, or similarly, if I do here not like 10 to the negative 5, but 10 to the negative 3, it's basically the same risk scale, and now I have again off. Yeah. So maybe what you said, it works for small time scales, but I mean, eventually you're gonna see that because of trend through exponent.
but it's a different mechanism, right? You have an external trend and you have internally a correlation, statistical effect, and you want to separate the two because there are two different mechanisms. One is global warming and for temperatures, and the other one is just statistical effects. Actually, it's in temperature data, the trend is global warming, and the autocorrelations are due to low and high pressure fields, right, that make the weather. So you have climate and weather in one thing, and you want to disentangle them. And this is and this you cannot do with the fluctuation analysis. You can do it with the next one.
Yeah. So that's why you have to basically detrend your time series before, and that's why we're gonna use detrended fluctuation analysis. Okay. Here is a nice picture how you can do this analysis. First of all, you have your signal. In this example, 1024 points, and then you split the signal again into non-overlapping windows. For example, here I have 4 windows with this number of points, and I'll look at here's a linear trend in every window, and I basically repeat this for small windows, okay, and calculate the residuals variance. So how much signal deviates from the linear trend, okay, and that's DFA1. So we do the trending with linear functions, but we can increase the order of the trending. Let's say we can take parabolas or cubic functions to fit this. But in our tutorial, we're gonna look at the trending with linear trends. Okay, and then for every window size, you calculate this residual variance, and then you average over the all windows, and that will give you 1 point in this log. Okay. And then you do it for different window sizes, and again, fluctuation function FFS scales with the window size. So the bigger the window size, the more signal fluctuates out of its linear trend. Okay.
What is the RMS?
It's root mean square.
It's the distance from the line to the point?
Yeah, and you square it and you take square root. Yeah.
But why? But if I
and then here is the examples of alpha 0.53, 0.99, and you can have even alpha larger than 1. Yeah, and now I did the same analysis. I mean, the signal is the same. Let me update it. Yeah, signal kind of the same, and now I have exponent that is closer to the correct one. work, you have to implement this different fluctuation analysis yourself. So don't use the of the shell solution. Just you have to split the signal into non-overlapping windows and then subtract a linear trend out of it, and then eventually we'll have.
Why there's such a big deviation? What is
I put here.
You put this at trend?
Yeah, 70. Yeah, I put the 0.5 here. And yeah, and I also have here original -5. Okay. So yeah.
But it should be independent of the trend. So if you increase the trend, it should still be okay. Right?
I think you should play with scales and windows that you have. Probably you have to add them to have more statistics.
Okay.
So yeah, here is the same. Yeah, and one very interesting thing is crossovers. Okay, so usually in real life data, you have different behavior for long Windowses and for large Windowses. For example, here, that's the electrocardiogram, is ECG for people who were in rest. That's the black one, and red one for people who basically were running on treadmill. Okay, and you can see here that the alpha, basically, that's the Hertz exponent of the same. Here's fluctuation function f of n, and here is the window size. Okay, and you can see that for rest and for exercise, these two scales differently. The same for long range. If you have longer Windowses, scaling exponent is different for those who were at rest and for those who did some exercise.
It's actually the same subjects, right? They are first in rest and
the same.
And then they let them run and then they show this that.
Yeah.
Okay.
And then people who had cardiovascular disease, something like this.
Yes.
They usually look like someone who who's doing exercise.
Yeah. You cannot distinguish
Yeah.
somebody who has heart disease from somebody who is running very energetically on the treadmill. They look very similar.
Yeah, that's interesting.
It's interesting because have you heard about marathon runners that die of sudden cardiac death during the race? Happens all the time, right? You have these people that running a marathon and then you're running what?
Yeah,
Half marathon. Okay.
I tried it.
Okay, and then so basically what you're doing is you're pushing your cardiac dynamics into a region of to somebody who has a congestive heart failure.
That's comforting.
But this should not lead to the conclusion like Winston Churchill that sport is smart, right? Or how do you call it? Sport is no sports, he said. Yeah, the German translation is that you murder yourself. No, this is the training effect, right? You push yourself out, but you're not all the time in this state. So your recovery basically afterwards brings you back to normal, to the black line. And if you train this, you get more resilient, Yeah. So like what they tell you.
That would be at zone 2 a lot of the time to recover.
Yeah, so this is not zone 2. So zone 2 is somewhere in between. Yeah. This is
zone 5 or something.
This is very on the limit here. So zone 2 would be in between there.
Yeah.
And what does this teach us? what they already tell you in the army, right? What doesn't kill you makes you stronger. And that's the proof of it. Okay, good.
Maybe later it causes a heart.
What?
I said maybe later on it causes a heart attack.
Yeah, if you sustain this for a long time, then it's I'm waiting until I read something about what's David Goggins, you know?
Yeah.
He pushes himself too much on people. Okay, different story.
Okay, then part D, we're gonna talk about Fourier transform and power spectrum. Basically, that's the definition of discrete Fourier transform. We know that its complexity is n squared, and then for most of applications, if you have complexity of algorithm that is n squared, you cannot compute something efficiently fast, and that's why people invented fast Fourier transform that has complexity n times log of n, and this saves you a lot of computational power, and it's much efficient. So now we're gonna play with Fourier spectrum. Here I have just simple sine with frequency of 2 Hz, and if I do with fast Fourier transform library, I'll calculate its spectrum. So basically, I do Fourier transform, and then I'll take absolute value square of this Fourier transform and normalize it by the length of the signal. I see that I have exactly one harmonic of 2 Hz. Okay, but here I have two parameters. First, I have the total length of signal, and the other one I have the
Sampling frequency.
sampling.
It's the inverse of the sampling frequency.
DT. So my question to you: what happens if I increase the length of the signal by a factor of 2? So now my new signal will be not from 0 to 5 seconds, but from 0 to 10 seconds. How will it change the power spectrum picture?
Twice as many data points.
It should lower the power because
No, still have the sine, but now longer, twice as long.
yeah.
Hey, just
No, but when
you have sine from 5 seconds, from 0 seconds to 5 seconds. Now you recorded it twice as long as previous sine. So what uncertainty principle tells you from quantum mechanics?
The more sure you are in one variable, the less sure you are on the second.
Okay.
so you have maybe additional.
How we can implement it here? Because it's very close to what you have for delta x and delta p in quantum mechanics. So here is kind of similar, right?
E times delta t,
Yeah.
and E is omega, right?
Yeah.
The frequency, so
Will go up the power.
Actually, if I increase it, then I'll have more points in frequency.
better
But
resolution.
the power,
Yeah.
the power at
Yes.
frequency 2 will be larger.
But
But
my
you normalize by the length, no? You normalize by the length?
it's normalized, but I think here is a half square, so
Okay.
now
Okay, good. But the important point is that you get better resolution.
now I have better resolution.
Longer time, better frequency resolution.
And then what will happen if I change the dt.
It will lower the power and make the resolution
It
greater.
depends if you enlarge it or decrease or increase dt. If you decrease, in the sense that you'd have lower gaps, you'd have more points,
Mhm.
and therefore I'd assume you'd have greater resolution. And the opposite if you increase it, in the sense that you have lower points. You still have the same time, so maybe you'd still have the same time period. So in like uncertainty principle wise, you'd still have the same ideas that we had just now.
Mhm.
Like the effect of t, of t and therefore y. But I think it would affect the resolution.
What about Nyquist frequency? What's this?
It's the bound of the frequency that you need to sample, like the steps that you need to sample.
In order to distinguish like frequency of 10 hertz,
Yeah, that's the cutoff.
yeah, our frequency of sampling frequency has to be twice as 10. So here we have a signal of 2 hertz, and our sampling rate is 10. Okay, so we will able to distinguish frequencies until 5 hertz, right? So if I do, let's say now, and change frequency of sine curve to 4, now I have 4, right? But if I'll do, let's say, 5.1,
6.
6, okay.
No, from a certain point you wouldn't have aliasing.
That's yeah. And I'm not sure we see this here, but
I think you should
Yeah,
have
we'll see
aliasing.
it in the fourth mark.
yeah, you see it. You see a
Because
lysing.
it flips like at the
Yes,
limit.
you see a lysing here.
Yeah, so here is like
Should be at 6,
4 hertz, but
there's a
yeah.
at 4, so it's folded in. Right.
yeah. But if you like make it smaller, then everything will be fine, because now you can resolve
Because the
frequencies.
bound increases.
You can resolve until 50 hertz. Everything until 50 hertz. Okay. Here is how original signal and inverse Fourier transform looks like. By the way, I forgot to mention that here I used half of the signal, and if I delete it, so I only plot here half of the signal. But if I do the whole signal, then it's gonna be basically similar for negative and for positive.
Why is this?
Because
you have
maybe
complex
all the left and
exponentials,
the right.
you need
The
to sum
complex
them up together to sign.
conjugate is the same.
Yeah, because if we have
Well,
like
sine you just
if-
have sum of two.
if
to
we
the
have
eye on it.
if you have real
Yeah.
function, then it's Fourier transform gonna be similar.
Yeah.
I mean, it's gonna be in
Together.
the same like a mirror image and the positive and negative frequencies. Okay. Here is a good demonstration of Nyquist frequency and the aliasing problem. So I have original blue signal of 8 hertz. You can see it here. Okay, and I also draw 2 signals with smaller frequency smaller than 16. Okay, for example, I have orange one with frequency of 9 hertz, and you can see that it basically goes through the same points of the original signal, but I can recover a different signal. Yeah, and the same for green one. So we have 12 hertz. Again, I'm kind of closer to the original one, but still, if I try to fit it with some frequency, I will not recover.
This explains the aliasing.
Yes. And what happens if I do here 16? What do you expect? How the signal of 16 hertz, the sampling of 16 hertz is going to look like?
Will be exact.
it be just a slower one? Because it would fold back to.
We're gonna have exactly
Zero crossings.
yeah. And of course, if we increase even more, then we will have more points in one period of signal. Okay. Now, I mean, even with 16, we're able to distinguish between those two signals. And if we have sampling rate that is higher than 16, so twice as this, then everything is fine. Okay. Yeah, I think the last part here is spectrum and how spectrum power connects with Hertz exponent. So usually when we have signal that we can zoom in and zoom out, power spectrum of them scales with the frequency as minus beta. And this beta connected with the Hertz exponent with this formula. So beta equals 2h minus 1. Okay. Why exactly this one? Because we know that h equals 0.5 produces white noise. Okay. So, and we know that power spectrum with white noise is basically a uniform distribution. Yeah. And if we plug in h equals 0.5, we have 1 minus 1, and it will give us basically 0. And that's the uniform distribution that we have. So here how it looks like for white noise. Basically h equals 0.5 and beta equals 0. Okay. We can improve basically statistics if we do averaging over many generations. And here I did the same, but for Hertz exponent of 0.75. That gives you beta of 0.5. You can see here slope, and these orange points is basically I averaged over this number of iterations, and it's always better to find a cutoff to make your feet robust. Okay. Yeah, and now the most interesting part of the tutorial is, can you make money out of this Hertz DFA analysis? Do you have some expectations? I mean, can we?
It depends. Did you already get your Ferrari or not?
You will never know.
Because you don't play.
I will
then
not
I
tell
can
you.
stop paying you a scholarship.
Okay, let's keep this question until we find out the answer. Okay. To analyze real market data, I have to use Yahoo Finance's library. So basically, I downloaded 3 things. The first one is S&P 500. The most successful and the companies, 500 companies of US market. Then Apple, why not? And the last one is Bitcoin. Okay. So I downloaded the data from 2025 1st of June, January, and till the yesterday. Yeah. Okay. Today we still have no data, so that's why we have time series of this number of points. By the way, do you know why there is a difference between a number of data points for S&P 500, Apple, and Bitcoin?
They probably closer on Shabbat, no?
Rishon.
Bitcoin, not what?
And Rishon.
Sunday.
And
Yeah.
Sunday, yes.
Yeah.
Yes. Is this the reason?
Yeah, Bitcoin is
Bitcoin is
trading
going all the
24/7,
Okay.
24/7, and then you have holidays.
Right.
Yeah.
Right.
And that's why you don't have really 65 days trading of S&P and Apple. But Bitcoin, yeah, only got. So here's graphs, S&P 500 price, Apple price and the coin price from 2015 till yesterday, and here the second graphs basically they shows you daily log returns is the difference the logarithm of difference in the start of the day and in the end of the day. Okay. And you can see that
Wait, what are the data points? It's the
price
at the start of the day and the end of the day?
you mean upper part or
The upper part.
upper part? No, it's just the price. Just the price, how price increases
okay.
with the time. Okay, I mean in 2015 you have price of S&P 500 about $2,000. Now it's something seven and 300. So, and here is the daily log return. So to calculate it, I just have a price of, for example, for S&P in the 8 a.m. and 6 p.m. So and I subtract them and take log. Okay. So and here is my daily log returns for all of them, and we can see that it's mostly distributed randomly, right? I don't have here any consistent pattern or so. And if I calculate autocorrelation function for all of these things,
You do have a pattern. The ups and downs
Which one?
come in the lower one. The ups and downs come in pairs.
this one,
Yes.
yeah, but it's
All of them.
It's not a consistent one, right? You have some of these points, but that's not what happens, in the most of the time. Okay? In the most of the time, you have one day you earn something, one day, you lose. So, but there are some events like, for example, this part is 2022 lockdown, and the world was scary if there would be a vaccine or not. So everyone just sold the stock market, and then I think that's one is Trump's tariff war with the rest of the world. So you can learn with this stuff geopolitics.
Why do we take the log returns instead of the log price instead of like the price and the returns?
You mean why do I need here a log?
Yeah.
It's just a better representation of this data to have it to have a more convenient like y-axis. But basically, it doesn't matter take a log or you take a log if you take a log or not. So you can keep just return. So basically, calculate the difference between opening price and closing price. Yeah. It's just the way as I did. You can do it differently, and maybe you will, you will have more money than I. So, yeah. And if we calculate autocorrelation function for just returns, we will see that it's quite looks like white noise, right? We don't have any pattern here. So if we go from if we analyze signal after 10 days, then it will not have any correlations with its past, right? But if we take absolute value of returns, you see that there is a pattern. So there is a autocorrelation memory in the signal when you calculate the absolute value of returns. It means that there is a volatility clustering, as you said. So when you have days, weeks, or months when price of stock like oscillates fastly, then you have either down of the price, and the same way you have uptrend and downtrend. So they somehow grouping together, and then you have just a regular regular uptrend, then nothing interesting happened here. Just look at the graph, and it doesn't fluctuate much. But then you have big crisis, and for this you have very strong price movement, either up or down, and that's what you see here. So absolute value of returns basically tells you volatility. And volatility is how it's like a measure how much your price can change.
So in the one case you take just your original time series when you go up, and then you don't have no memory, and in the other case you do an absolute.
I calculated it not for time series, but for the log returns.
For the log returns,
Yeah.
right.
Yeah.
But in the one case you do just from the original time series, I mean from the log return time series, in the other case you do an absolute. You don't look at the minus.
I don't care either it's downtrend or uptrend. I just I care only about the absolute value of it.
Absolute change.
Yeah, absolute change.
Yeah.
And so
volatility.
Yeah, and now the question is,
Yeah, but that's important if you actually want to invest.
That's important.
Because then you know when to sell, when to invest. So
Exactly.
you couldn't use that actually.
We're gonna see it in a minute. Okay. So, and when we calculate autocorrelation function, we can also try another method with Hurst exponent. Okay. So we can apply the trend fluctuation analysis to market data and calculate Hurst exponent, right? And if we do so, for just returns we have almost h closer to 0.5, means that it's just a white noise and signal without any memory. Then for absolute value of returns we have some persistence, so it means that this volatility class 3, and if we shuffle the returns, so let's say we have this log returns, and then I just randomly shuffle the whole data. So I have, if there is a true time series, I have to destroy its temporal structure, and I expect for shuffle data also values of Hurst exponent closer to 0.5, and that's, you can see that's true. Okay. But now the question is, here we calculate the Hurst exponent, just taking the whole period. Okay, here we have data of 11 years. Okay, so maybe it's not a good way to predict how market will move to taking into account the whole period. Maybe we should just use some rolling window. Let's say we pick a period of 1 year, we calculate the Hurst exponent, and then we change it. I mean, we shift it by some value, and then calculate again. Maybe that's gonna be more efficient way,
How do you decide the window size?
Arbitrary. So it's purely heuristic. You can play with it. So here I used window size of 300 days. So basically, it's almost a year. I mean, trading year even less, because you have weekends and holidays. So I took your window of 300 days and a step of 5 days. So every trading week I shift my window. Okay, and here is result. Okay, so what we can see here for S&P 500, look at the structure. In some periods I have this Hurst exponent greater than 0.5, and some of the days I have Hurst exponent smaller than 0.5. Okay, so it means that, but you see that it fluctuates a lot, but we can build a strategy of trading. I mean, we know that if H is greater than 0.5, there is a positive autocorrelation, meaning that signal or time series is persistent. So if it grows, it keeps growing, and if it h smaller than 0.5, it's the opposite, right? If time series growing, then there is a high chance to change the direction, to change the trend to the opposite. So, and our trading strategy gonna be the same. So if we calculate the Hertz exponent and it's greater than 0.5, we copy the pattern from the previous day. Let's say here, for example, we see that the day before S&P 500 went down. So we calculate Hertz exponent. If it's greater than 0.5, we just sell the stock and do short. Basically, we expect that it will continue to go down. Okay. If we calculate here Hertz exponent and it turns out that it's smaller than 0.5, we do the opposite. If last day, the day before S&P 500 went down, we buy it and expect that it will do the opposite thing today. It will go up. Okay, that's gonna be our strategy. And as a benchmark, we just do a simpler strategy, buy and hold. Okay, so we compare the Hertz strategy with buy and hold strategy. We just buy and hold. We just one day we buy stock or some S&P or Apple. Okay, and we wait.
And the random strategy.
And the third one is random. So we just do randomly buy and sell. Okay. So and finally, you want to see the results? Okay.
Oh, you're putting us so much.
Here's the picture. Okay. So buy and hold strategy 1, and Hertz exponent, you see, it goes down.
So we didn't buy your Ferrari.
Yeah, I did.
And bias this?
Yeah, the right
Maybe the window wasn't right.
Maybe, yeah. Again,
It's
it's purely heuristic window size, heuristic shift. But there is some good pattern that you can see here. For example, this drop is approximately between 100 and 115.
COVID.
Yeah, you can see that buy and hold strategy loses money at this period.
Yeah, I
right?
think our algorithm
what-
is more greedy in the sense that it does what it thinks best at the same time, but it doesn't really look at the future, you know.
Yeah, and you can see that her strategy basically earn a lot of money here, right? So while
It's a greedy algorithm in a sense, or heuristic.
yeah,
But it
Yeah.
does only local decisions.
yeah, that's one of the problems. The other problem with this her strategy is that you also have to pay commission to your broker. So buying and selling your shares is not for free. You have to pay commission, and in the long term, it will sums up to
A lot of fees.
yeah, sums up to real money, not just 0, 1, not to 1 cent. I mean, if you do it for like here for 11 years, this every cent will sums up, and yeah.
Is this benchmark on the trended data or the trended data or the
Which one? Buy and hold or
both?
Sure.
Like, are they like did we simulate? I mean, I assume both are on the same data. Like,
Yeah, S&P 500, yeah. And the buy and hold strategy, I just bought it in 2015 and just I hold it. I did nothing. But her strategy, I did the trend fluctuation analysis in order to calculate her response, because obviously in market data I have a trend, and
But
it's always upward trend.
Yes,
So-
because the market is like always growing. So like
Yeah.
that's why the buy and hold. If we simulate it on the trended data, then maybe the Hearst strategy does work.
Yeah, but who
But
cares
volatility,
about simulated data?
Yeah, but if we
Wanna
can
make
get
money,
the
right?
trend and the Hearst exponent, then we can find the criterion where it is more optimal to hold our stocks, and because with the Hearst strategy we sell very often, we don't capitalize on the trend of the market, and only on the local price fluctuations. So we need to make a there's a critical point there where the trend is more beneficial than the price differences.
Yeah, you can see it by the way here. So I think 90% of the really sellers and buyers in the current financial market, they are robots. It's not real people. And in the crisis period, you see they can make a lot of money out of it, right? So if we just use this Hertz exponent strategy with combination of buy and hold, we can sure gain some money, earn some money. So that's why probably you have to play with that, do some combinations.
So your homework will basically be
To beat the market.
to beat the market and come up with a strategy to earn money, and the one that earns the most money will become our financial analyst of the department. Okay. Not of the,
I think
not
he would
of
just
the
be his
department,
own,
of
and then
my
he would
personal financial.
Maybe try Bitcoin. It seems to have a better exponent.
Yeah, Bitcoin, because Bitcoin is not as efficient as S&P 500 and Apple and other. I mean, if one strategy will work, everyone will use it, and no one will earn money because everyone if there would be like one pattern that you can make money, then it won't be the case for.
Do you see the COVID also in Bitcoin? Can you go back? Or you only saw it in Apple?
No, I think. Yeah, it's kind of correlated a bit.
So it's also there.
Yeah.
But is it? You said it's.
I don't think so though, because the entirety of Bitcoin.
Which one is the COVID? COVID was
1500.
1500. There before 1500. In Apple it's a little bit, because people have to buy computers for Zoom, so it didn't affect it too much.
Yeah.
And
I think Zoom has the opposite. They
Zoom
they
went
blow up.
Yeah,
they blow up because of
yes.
people go online.
Now everybody's using
yes.
Zoom.
Yeah.
But where does it translate to Bitcoin?
It's a small dipping.
You think it's this one? But it's not 1,500 because you have 1.5, so it's at 1,000. It goes up actually. Is this? Because you have a factor of 1.5 difference in the time resolution.
Yeah.
I think it should actually go up because everybody's just
Had more time
because they do it on their own computers at their own houses.
COVID is like at the 1 to 50 mark, so it's like not really changing there. It's like 1/4 after the 1,000.
Okay. Right. But for Bitcoin it goes up, no? Or it goes up.
Yeah.
But I have a question about we saw that the H is approximately half, right?
Yeah.
But wouldn't we expect not just white noise? I mean, like for example, geopolitical instances that have some influences like wars, let's say Hormuz, right?
Yeah.
Wouldn't that actually not be just white noise? An actual like influential specific noise?
But they don't happen. I mean, they don't cause a trend. They're sort of
Events.
No, but
Yeah,
if
they
it
happen.
cause
Yeah.
collapses,
The only thing they cause is the volatility increase. So prices become, the amplitude of change of the prices increases for some period of time, and then it stabilizes. Yeah.
Would be interesting to
but
check out.
artillery, for example, or military like tech stuff.
Yeah.
So maybe it's not in the S&P. I don't know, but that would cause a trend, wouldn't it?
Yeah,
For
because
both, yes.
they make money out of it.
Yeah.
But one thing is now you can watch, I don't know what is the index of Iran, but after they get their 300 billion from Trump, you can, this would be interesting to study how their market goes up and the age exponent changes. I guess a lot,
Yeah.
unfortunately for us. Yeah.
Yeah.
But it would be interesting.
Yeah. So that's it for today. Yeah. Thank you for
Good.
coming.
And
It was the last
homework will
last,
be posted
lesson. Yeah.
soon.
We're gonna post it, and you will have 2 weeks as usual to complete it.
So it's best of 4?
Hmm?
Best of 4?
What is the form?
In normal.
No, everything. Yeah. Right. It was generally good. I mean, all the grades were quite good.
Yeah.
I mean,
We're gonna see.
they're going. I thought you told me that they were all time about 90, right?
Except the first one.